There's actually an interesting relationship between the angle of incline and the coefficient of friction. And it's a good way to determine the coefficient of friction, or at least approximate it, if you don't know anything about the materials involved. So let's picture a box on a slope with angle theta. And angle theta is going to be the angle from the horizontal. So let's draw our box. Oops, let's use white. We'll draw our box here for our free body diagram. And let's establish our convention, our sign convention, being up the ramp as our positive x direction and perpendicular to the ramp as being our y direction. So what forces do we have acting on this box? So first of all, we're going to have a gravity force, or force of gravity, which we know the magnitude of that's going to be m times g, right? Mass times the acceleration due to gravity. We know there's going to be a normal force, right, which is going to be in the y direction. And in this case, we'll assume that there's a friction force as well, right? A friction force going opposite the potential motion of the box, right? So it will be up the ramp. So if we're considering coefficients of friction, let's assume the case of the box sliding down the ramp at a constant speed. So what's going to pull the box down the ramp? So we know the only thing that's going to pull the box down the ramp is this force of gravity. And more specifically, it's going to be the component of the force of gravity in the x direction, in the down the ramp direction. So let's show those components of that gravitational force. We're going to have the y component of that and the x component of that. And if we want to put the magnitudes of those forces, we can just write this magnitude here as this is going. Remember, this angle in here is also theta, right? Because of similar triangles and parallel lines. So this blue angle here is going to be mg cos theta, right? And this red vector here is going to be mg sine theta. Right? And it's going to be this force, this component of the force that's pulling the box down the ramp. This here is just going to equal essentially the normal force, right? Now the case I mentioned, the case that we're going to take is the case where let's assume the box is sliding down the ramp at a constant speed. If the box is sliding down the ramp at a constant speed, I'm actually going to write that. Constant speed. What do we know about this situation? Well, we know if it's moving at a constant speed, the net force has to equal 0. And if the net force has to equal 0, the x components and the y components have to sum up to 0. So we already know that this component here, the y component here of the gravity, and this normal force are going to be equal and opposite to each other. They're going to cancel each other out. And for the box to be sliding down the ramp, this force of friction here, right, the force of friction, we know that that's going to have to equal this component of the gravity force for them to cancel out, right? So essentially what we're saying is gravity and friction cancel each other out, so we know that the force of friction is just going to have to equal this value, right? Remember, the whole point of this is that we're trying to find out a relationship with the coefficient of friction, right? So let's just remind ourselves, what is the coefficient of friction? In this case, we're talking about the kinetic friction because the object we said is moving at a constant speed. It's sliding down the ramp. But remember what that equals. That's going to be the friction force over the normal force, right? Now, in this free body diagram, we know that the friction force is going to equal mg sine theta. It's going to equal this x component of the gravitational force. And we also know the normal force is just going to equal this mg cos theta. So can't we just substitute these values into this kinetic friction formula? We can. Let's see what happens if we do that. So the force of friction was m times g times sine of theta. And we're going to divide that by mg cos theta. You might see where this is going already if you're remembering your trig identities. Notice how when we do this, the m and the g are going to cancel out. And what that tells us is it actually doesn't matter what the mass or the acceleration due to gravity are, this will always be true. So mu k, or our coefficient of kinetic friction is just equal to sine theta over cos theta. So all this is saying is that the only thing that determines what the coefficient of friction is r theta, or the angle of incline that makes the box move at a constant speed. That's the key. This only works if the box is moving at that constant speed. Now, there's actually an identity, a trig identity, which can further simplify this formula. You might know that sine over cos of an angle is just the equivalent thing as saying tan of an angle. Those are equivalent statements. So we have this beautiful expression here, mu k, or the coefficient of kinetic friction, is equal to just the tan of the angle. And that angle, remember, this is important, this is the angle in which the object is moving by itself at a constant speed, just due to gravity. So it's moving at a constant speed. Okay? So if we have a simple setup of an object sitting on an inclined surface, if we find, and we're able to play with that angle, if we find the angle that that object will move at a constant speed, so it sort of moves down the ramp at a constant speed by itself, just due to gravity, all we need to do is take the tan of that angle in degrees. We'll use degrees in this course, and that gives us our coefficient of kinetic friction. Pretty simple, right? Now, you can actually do the exact same thing for the coefficient of static friction. And static friction is, remember, it's the friction that needs to be overcome if you want to start an object moving. So if we have the exact same setup and the exact same free body diagram, in fact, let me copy that. The exact same free body diagram, let's draw it over here. And this time, we're not looking at the box moving at a constant speed. We're looking at, you're increasing the angle of the slope, for example, and you increase it so much when the object is still, you basically keep track of the angle that the object starts moving. Like the instant the object starts moving, that's the angle you keep track of. Because at that moment, the same thing will have happened. The gravitational force, or the magnitude of the gravitational force, and the force of friction will have equaled each other and canceled each other out, basically. So when the object starts moving, the force of static friction is overcome by the force of gravity, and it starts to slide. So in order to find our, and all the calculations are exactly the same, right? Because we know it's going to be mu s is equal to our force of friction over our normal force. And if we do the exact same simplification, we'll get that the mu s is equal to tan of theta. But this time, theta is the angle at which the object starts moving. Right? Because that's theoretically, the object should start moving when the friction force, the static friction force, is overcome by gravity. So that's an easy way to calculate or to determine empirically through experiment the coefficient of static friction and the coefficient of kinetic friction just by playing with the slope that an object is sitting on.